Swayam Prabha. Digital India. Educated India.
I am Professor Rajiv Mishra, working at Computer Science and Engineering Department, Indian Institute of Technology, Patna. The title of this lecture is Computation Offloading in MEC. Let us review the MEC architecture on which we will be talking about later, the computation offloading. So, what we have seen is about MEC architecture, that is, there are several MEC concepts that are built upon with the purpose to smoothly integrate the cloud capabilities into mobile network architecture. Therefore, there are various possible architecture of MEC such as small cell cloud, mobile micro cloud, fast moving personal cloud, follow me cloud, concert, and finally, a standard HC has considered many of these ideas and made a standard for MEC called HC standard. Let us understand these MEC architectures. So, for MEC architecture, which is called small cell cloud SCC, here was introduced in 2012 by European project, which is called a Tropic. Here it is to enhance the small cell SCENB, they are called. So, they are just like micro cells, pico cells, femto cells, and here how they are going to enhance is they are providing additional computation and storage capabilities along with these particular cell, and thereby integrating this additional cloud computation and storage capabilities in these particular cell. Therefore, it is called a small cell cloud. Now, the cloud enabled in small cell ENBs, they support the edge computing in the following manner. So, the cloud enhanced SCENBs can pool their computation power exploiting the network function virtualization. So, these are the methodologies how they are going to enable the additional cloud capabilities with these cell. Now, the computing resources are virtualized by means of virtual machines located at these cells, that is SCENBs. Now, because the high number of SCENBs to be deployed in future mobile network, the small cell cloud architecture can provide enough computation power for user equipment, especially for services and applications having stringent requirement on latency. Now, in order to fully and smoothly integrate SCC concept into the mobile network architecture, a new entity called SCM is introduced to control SCC. So, SCM is in charge of the management of computing and storage resources provided by. So, here we can see that this is SCM, and this particular SCM or a manager, small cell manager, is now going to control this SCENBs, and SCENBs are having these additional cloud capabilities. Now, SCM is in charge of the management of computing and storage resources provided by SCENBs. Since SCENBs can be switched off and on, therefore, this SCM performs dynamic and elastic management of the computation resources within SCC. So, whether it is off or on, so this particular, it is the responsibility of SCM to perform dynamic and elastic management of computation resources within SCC. So, SCM is aware about the overall cluster context, that is both radios. So, this comprises of the radios and the cloud wise. Inside that, the cloud is also there and decides where to deploy the new computation or when to migrate an ongoing computation to optimize the service delivery of the end user. So, here this becomes quite important that the compute and storage are with these small cells, and these small cells are now controlled by the small cell manager in a small cell cloud. Here we can see that small cell manager can be deployed in centralized manner, either as a standalone SCM located within the RAN radio access network, which is shown over here close to the cluster of SCNBs. Here it is shown that this is SCENBs, and you can see that here it is being added additional computing and storage capabilities or an extension of MEMEs. And these SCENBs, which is having the additional computing and storage, are often controlled by SCM, that is what is shown, and SCM is centralized, working as a centralized control. Now, this SCM has two functionalities. One is that SCM is now having an control with the coordination of RAN or RAN, that is radio access network. So, the other one is that these SCM is also having the control with the core network. Of the cellular network. This is radio access network. Now, when you come to the core network, so core network and this particular terminologies of a core network is about the mobile network. So, we are going to see the integration of the cloud or the compute and the storage inside these particular cells, which is the part of RAN, and to control it, it requires SCM, and SCM part in RAN will make this kind of functionality available to the core network in the control of a core network. The other control of SCM is with the core network. Now, if you see this particular core network, it has the following components working in coordination to realize this mobile network. So, we are going to see the core components, core network components. So, core network components are MME, that is mobility management entity. So, mobility management entity keeps track of the user equipment if it moves from one cell to other cell in this particular mobility, it keeps track of all that user equipment mobility. Now, other one is called HSS, that is home subscriber server. It keeps all the credentials of the subscriber, that is the user equipment which are using the mobile network. Third important thing is serving gateway, SGW, that is when the incoming traffic or let us say the mobile user or user equipment connects it. So, it has to go through this serving gateway, whereas packet gateway deals with the transport of the messages or the information. So, therefore, these particular to take these particular aspects with or to have the coordination with these aspects of the core network, the SCM, that is small cell controller, small cell manager, will interact with the core network. So, SCM in core network is one component of SCM, and SCM in RAN network will manage the cloud inside small cell cloud. They are called small cell cloud. So, therefore, this is the positioning of small cell manager, that is called the centralized SCM configuration. Now, let us see that. Let us review that SCM can be deployed in a distributed manner, where the local SCM, that is LCM, this you can see, or a virtual LCM, VLLCM, manages the computing and the storage resources of this SCENB. So, here you can see that this is the compute and storage is with SCENBs, that is inside the small cell. So, of SCENBs, a cluster in the vicinity, while the remote SCM, this is the remote SCM or SCM called remote SCM, while remote SCM is located in the core network of the mobile network, has the resources of all SCENBs connected here at its disposal. So, you can see that the remote SCM deals with or work in coordination of the components of the core network, that is MME, that is mobility management entity, then HSS, that is home subscriber servers, which contains all the credentials of user equipments, and then serving gateways and the packet gateway. Now, the next architecture of MEC is mobile micro cloud or MMC. So, let us see that this mobile micro cloud, what components are there in the RAN and CN, and how it integrates that storage and compute facilities. So, MMC allows the users to instantaneously access the cloud services with a low latency, that is why it is with ENB, or it is with the base station of mobile network. This particular cloud is being formed, therefore, it is called a mobile micro cloud MMC. So, here we can see that MMC user equipment exploit the computation resources of single MMC, which is typically connected directly to the workstation wireless base station, that is ENB in the mobile network. Now, MMC concept does not introduce any control. There is no control which was there in SSC, and the control is assumed to be fully distributed in the similar manner as VLSCM in SCC. Okay, so, MMC are interconnected directly or through the backhaul in order to guarantee service continuity if user equipment moves within the network to enable the smooth VM migration among the MMCs. So, that is all having said, let us go to the next review the next architecture of MEC called fast moving personal cloud. Now, in this architecture, this integrates the cloud services into the mobile network by involving the technologies called software defined network and network function virtualization. Now, compared to the other methods, this MobiSCUT is not directly at the access nodes. You can see that access nodes do not have that cloud or ENB, but at the operators cloud located within the RAN or close to the RAN. So, you can see that the cloud is being formed here away from the base station inside so it will be located within the RAN or close to the RAN, but not in the core network. So, these clouds assumed to be highly distributed, as in case of SCC and MMC, enabling the cloud service to all user equipments in the vicinity. So, MobiSCUD introduces the new control entity, that is called MobiSCUD control. So, this is called a MobiSCUD control, full form of MC, which interfaces with the mobile network. So, you can see that this interfaces with the mobile network, SDN switches, this interfaces with the mobile network, this is called mobile network, then SDN switch, here this is the SDN switch and the cloud. So, it will be now having the integration with the mobile network, also called a core network, and then it will now integrate or interface with SDN switch, and thirdly it will interface with the cloud of the operator. So, this is a very important control in realizing the fast moving personal cloud, that is MobiSCUD. Basically, the MobiSCUD control has two functionalities: monitoring the control plane, that is how the monitoring is done is by sending the signaling message exchange between the mobile network to be aware of the user equipment activity. Second one, it says that it will do the orchestration, that is it will manage this particular cloud, orchestrating and routing the data traffic within the software defined networks, enable transport network to facilitate the application offloading and virtual machine migration if the user equipment moves throughout the network. Next important review is about Follow Me Cloud FMC. So, Follow Me Cloud FMC, let us understand, is that the cloud services running at the distributed data centers. So, here it is called distributed data centers. So, you can see it is not a single data center, but several data centers, therefore, it is called the distributed data centers. Follow the user equipments as they roam throughout the network. So, the user equipment as they roam around the network, so these particular cloud services, that is the distributed data center, they have to follow it. So, if for example, if the resource is allocated in one data center and it moves to the other one, then VM, these resources are in the form the VM migration will happen, and therefore, it requires a particular control for doing this virtual machine migration as the user equipment moves from one ENB to other ENB in that location. So, when compared to the previous MEC concepts, the computing and the storage power is moved farther from the user equipment. You see that this particular data center is often very distant compared to the previous methods. So, nevertheless, like while previous MEC assume a centralized core network deployment, the FMC leverages from the fact that the mobile operators need to decentralize their network to cope with the growing number of user equipments. So, therefore, this distributed data center enables the scalability. Now, there are three centralized core network used in the current network deployment is assumed to be replaced by one distributed. So, here you can see that there is a distributed one. So, here we have to see that the components of the core network is now distributed. It is not one serving gateway, but rather distributed form. It will be replicated at more than one ENBs, for more than ENBs. So, similarly, it will be a packet gateway that also is to be done. So, instead of 3 centralized core network is used in the current network deployment is assumed to be replaced by a distributed one. So, this is a distributed one. So, for convenience of mobile operator, the distributed or a data centers may be located at the same place as the distributed serving gateway or the packet gateway. So, maybe that here you can see that the for each serving and packet gateway there is a data center. For each serving packet gateway there is a data center. So, that is why this follow me cloud often is located with the mobile operators, that is in the mobile network at the core. Now, follow me cloud introduces new entities in the network architecture called DCGW. Now, DC means data center and GW is the serving gateway. Mapping entity is to be done and FMC controller deals with that. So, these can be either functional entities co-located with existing network or as the software runs on. So, DC GW mapping entities maps the data center to the distributed P/G, that is packet or the serving gateway according to the various metrics such as the location, hop count between the data center and the distributed core network in a static or in a dynamic manner. So, FMCC, that is follow me cloud, manages the data centers computation and storage. The cloud services running on them and decides which data center should be associated to the user equipment using the cloud services. So, this is very well organized in this particular manner. So, FMCC may be deployed either centrally or hierarchically with the global FMCC and the local FMCC for better scalability. FMC itself may be decentralized control by omitting the FMCC altogether. In such cases, DC coordinate themselves in a self organizing manner. Let us see the next MEC architecture, that is the concert. So, concert is the concept converging cloud and cellular network. So, concert assumes to exploit NFV principles and SDN. Like other methods, computing and storage resources are utilized by both conventional mobile communication and the cloud computing services presented as the virtual services. So, the control plane consists of the conductor, which is the control entity managing communication, computing and the storage resources of the concert architecture. So, the conductor may be deployed centrally like here or in a hierarchical manner. Data plane consists of the radio interface equipments and physically representing the ENBs, SDL switch and computing resources. Now, the computing resources are used both for baseband processing similar to CRAN and for handling the application level processing, that is application offloading. So, concert proposes hierarchical placement of the resources within the network to flexibly and elastically manage the network and the cloud services. Now, the local servers with a local servers with a low computation power are assumed to be located directly at the physical base station, and if the local resources is not sufficient, regional or even the central resources, central servers are being exploited. So, this is quite a standard way of reducing the latency in concert scheme. Now, let us review about the MEC architecture, which is proposed by IIT, that is MEC. So, IIT is currently deeply involved in the standardization activities in order to integrate the MEC into the mobile network. So, MEC can be exploited either by the user equipment here located directly in the user equipment, either by the user equipment application, or by the third party customer via customer facing service portal, CFS portal. So, either of them can exploit the MEC by either the user equipment application or the customer facing service portal. Now, let us say that what happens next. Both UE and CFS portal interact with MEC. So, now they have started interaction through MEC system level management. So, they have to interact with MEC through MEC system level management. Now, MEC system level management will include the user application lifecycle proxy, which mediates the requests such as initiation, termination or relocation of user equipment application within MEC system to the operation support system of the mobile operator. Now, OSS will decide if the requests are granted or not. So, it has to decide if the request is granted, then it will move to the next level, that is mobile edge orchestrator. If not, then it will not be executed in MEC. Now, once it comes with the mobile edge orchestrator, while the requests are being granted, then let us see that mobile edge orchestrator is one of the core functionality in MEC. The system level management as it maintains overall view on the available computing resources and the MEC services. So, mobile edge orchestrator allocates the virtualized MEC resources to the applications that are about to initiate depending upon the application requirement. Now, for that orchestrator also flexibly scale up and down the resources. MEC system level management is interconnected with MEC server, and this MEC server level management here consisting of a mobile edge platform and a virtualization platform manager. So, therefore, MEC system level management manages the life cycle of the applications through the traffic rule, and application server management is responsible for allocation, and MEC server represents the virtualized resources and hosts the MEC application running as virtual machine on top of the virtualization infrastructure. Now, after understanding, let us come to the topic called computation offloading in mobile edge computing. So, the critical use case regarding the MEC is the computation offloading, as this can save the energy and speed up the process of computation. So, the crucial part regarding the computation offloading is to decide whether to offload or not to offload. So, here that is shown over here, the user equipment is deciding to do everything, all computation of the application on the device itself, or it will offload to the mobile edge computing for performing the computation. So, in the former case also the question is how much and what should be the offloaded. Now, the decision on computation offloading may result into the local execution. If it is decided not to offload, the whole computation is done locally at the user equipment. So, the offloading to the MEC is not performed here in this particular case, that is called local execution. Second part is called full offloading, that is the whole computation is offloaded and processed by MEC. So, here the example is shown as the full offloading. That means, the user equipment offloads the entire computation to the MEC and it will not do anything, it will not execute it there. Here everything is done on the user equipment and there is no offloading done over here. Third one is called a partial offloading. In partial offloading, you can see that a part of the computation is processed locally. Here this is to be done locally and another part is to be offloaded to the MEC, and this is called a computation offloading in MEC. Either there is no offloading, if it is a offloading then it is a full offloading or a partial offloading. There are three different type of computation offloading is done. Why the offloading is done is to save the energy and also speed up the process of computation. Now, computation offloading in MEC. So, computation offloading, that is a partial offloading, is very complex process affected by several factors such as user preferences, radio and backhaul connection quality, user equipment capabilities and cloud capabilities, resource availability. Now, so the important aspect in the computation offloading is also an application model or type, since it determines whether full or partial offloading is applicable and what could be offloaded. So, these are all different aspects of the computation has to be collected and then only decision has to be made whether it is to be offloaded. If it is offloaded, then it is to be offloaded full or partial. For partial, lot of other details are to be collected such as user preference, radio and backhaul connection quantity, user equipment capabilities, cloud capabilities, resource availability. So, we can classify the application according to several criteria. Offloadability of application. So, the application enabling the code or data partitioning and parallelization, that is the application may be partially offloaded, can be categorized into two types. The first says that the application which can be divided into the fixed number of offloadable parts that all can be offloaded. Now, since each offloadable part may be differ in the amount of the data and required computation, it is necessary to decide which part should be offloaded to MEC. The second part is that application which are always composed of some offloadable parts and some are non offloadable parts. So, here you can see through an example that in this particular application you can see the subdivision or the parts, let us say 1, 2, 3, 6, 9 are processed locally, and offloadable parts such as after 3, 4 will be executed offloaded, 5 and then 6 will be executed here and then 7 will be offloaded, 8 and after that 9, after 9 the next part will be offloaded, that is 10. So, you can see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, in this offloadable 4 then 5, then 7, then 8 and then 10. They will be offloaded, and the rest are not offloaded. Why? Because they may not be offloadable. If they are not offloadable, for example, if you are taking the user input, it cannot be offloaded. It has to be with the user equipment. So, user equipment, user is typing something, so that will be processed locally. So, therefore, the computation offloadability of the application need to be determined, what can be offloaded, what cannot be offloaded, whatever is offloaded called offloadable or offloadability of the applications. Out of that, you have to decide whether you want to process locally or it is to be offloaded. Take this example here, it contains, the application contains two parts, one is called non offloadable. So, it cannot be offloaded, but it has some other offloadable components or the parts. So, other offloadable parts are now decided whether they have to be processed locally or it is to be offloaded. For example, here the component or the part of the application 1 is offloaded, where 2 is not offloaded, it is executed locally. Then 3, 4, 5 is offloaded, where 6 is done locally and 7 is also done locally, where 8, 9, 10 they are being offloaded. So, I think that what we have explained you about the offloadability of the application and several criteria are now very much needed. So, it is a very complex method or procedure of computation offloading. Now, knowledge on amount of data to be processed. Now, the application can be classified according to the knowledge on the amount of data to be processed. So, for the first type of the application, which is nothing but represented by the face detection scan, the amount of data to be processed is known beforehand. Now, another type of applications, that is called second type of applications, where it is not possible to estimate the amount of data to be processed, as these are all continuous execution application and no way to predict how long they will be running, such as online and interactive. So, the knowledge on amount of data to be processed, sometimes it is known depending upon the application, such as face detection viruses can hear the amount of data to be processed known beforehand, but there are certain type of application where the amount of data, knowledge on amount of data to be processed is not known. Now, dependency of offloadable parts. So, once we decided that there are some parts in the application which can be offloadable. Now, then let us see the dependency of the offloadable parts. So, offloading obviously depends on the mutual dependency of individual parts to be processed. So, the parts of the application can be either independent on each other or mutually dependent. So, in the former, all the parts can be offloaded simultaneously and processed in parallel, whereas the later case, if they are mutually dependent, the application is composed of the parts that need input from some other parts, or parallel offloading may not be possible in that case. So, note that the relationship between among the individual components can be expressed with the help of component dependency graph CDG, or called a call graph. So, component dependency graph, one such example is shown here, you can see. So, let us see the example that whole application is divided into m non offloadable parts. That is, here in this example it is shown as 1, 4 and 6, they are non offloadable parts, non offloadable, called non offloadable parts, and n offloadable parts. So, they are called 2, 3, 5, they are offloadable and they are offloadable. Now, in this case 2 and 3 here, 2 and 3 can be offloaded only after the execution of 1. So, let us say that 2 is dependent upon to complete the execution of 1. So, 2 is dependent upon 1 execution of 1, while 5 can be offloaded after the execution. 5 is dependent upon this, that is 3, and 5 is dependent upon 4. So, you can see that this particular dependency can be depicted by the graph called component dependency graph, the example which we have seen over here. Now, the other important aspects regarding the computational offloading is how to utilize and manage the offloading in practice. Now, user equipment need to be composed of the code profiler, system profiler, and decision engine. Code profiler is responsible for determining which could be offloaded. System profiler is in charge of monitoring various parameters such as available bandwidth, data size to be offloaded, or the energy spent by the execution of the applications locally. The decision engine determines whether to offload or not, and in case of offloading determines the location to be offloaded, called decision engine. So, all three things user equipment is required, that is code profiler, system profiler, and decision profiler. Now, decision on computation offloading in MEC. So, the main objective of the work focused is the decision. So, this particular decision on the computation offloading is based on to minimize an execution delay, is based on to minimize the energy consumption at the user equipment while predefined delay constraint is satisfied. And to find a proper trade off between both energy consumption and execution delay. Now, let us see about one by one what do you mean by minimization of execution delay. So, one of the advantages introduced by computation offloading to the MEC is the possibility to reduce the execution delay, that is called D. Now, in case the user equipment performs all the computation by itself, that is no offloading, the execution delay, let us say that D1 represents solely the time spent by local execution DL at the user equipment. So, here you can see that it is DL, here it is DL, that is local. Now, in case of computation offloading to MEC, the execution delay is, let us say, D0. So, D0 means offloaded. So, this is the execution delay in case the computation offloading to MEC, the execution delay. So, let us see how are you going to calculate the execution delay, that is DO of offloading. So, that involves three different factors: transmission duration of the offloaded data, that is DOT, then computation processing DOP, and then time spent by the reception. So, let us understand this particular formula. D of offloading, delay in the offloading, execution delay is computed as the transmission duration of the offloaded data to MEC, that is DOT, transmission delay of the offloading, and the computation processing at the MEC is D processing, and then another factor called time spent by the reception of the processed data, that is DOR. That is, it is for sending the data to the edge. This is called communication delay, and also the receiving the data from the edge, that is also a communication delay, and third one is the computation at the edge, that particular delay, and total delay is the execution delay of offloading. So, it could be observed that user equipment E or UE1 performs all the computation locally. So, you can see that it is red, that means all the computation is to be performed locally. Since the local execution delay is significantly lower than execution delay. So, if di is less than do, that means if you consider that the delay is quite less than sending it to the than offloading it. So, it using this particular equation, that if it is sending the data, that is O, it is more, and the delay to execute or to compute at user equipment it is less. So, less delay means that it is taking the decision for local execution. Contrary, a better alternative for user equipment 2, whereas for user equipment 2, let us say another example, to fully offload the data to the MEC as the local execution would result in a notable higher execution delay. So, for example, here the decision says that if let us say that so notably higher execution time. So, here so this one is more. So, here you can see that contrary, a better alternative for user equipment 2 is to fully offload the data to the MEC as the local execution would result in a higher execution delay. So, if it is to be done locally L, it is having higher delay, local execution has higher delay compared to doing it offline. So, doing offline is less. So, the decision is to offload to the MEC. So, what it does is it has offloaded data to the MEC and there it performs the operation. Let us say that it will execute with DOP time and then result sends back result, that is DOP, and total delay is less than if it would have happened at local end. Therefore, the decision is to offload to MEC. So, here the computation offloading decision itself is done at the UE by means of computation offloading policy module. So, computation offloading policy module, now it will decide about whether the delay based on this particular delay, whether the delay of executing locally is less or it is executing at the remote or at the edge is less. So, whatever is less, this computation offloading policy module. So, this particular module decides during each time slot whether the application waiting in the buffer should be processed locally or at MEC while minimizing the execution delay. Now, minimization of energy consumption while satisfying the execution delay. Now, let us see that having computed the execution delay constraint. So, let us see how are we going to minimize the energy consumption. So, main objective is to minimize the energy consumption at user equipment while the execution delay constraint of the application is satisfied. On one hand, the computation offloaded to MEC saves the battery of the user equipment, since the computation does not have to be done locally. On the other hand, the user equipment spends certain amount of energy in order to transmit the offloaded data to the computation, and let us see that that is called E of OT. Similarly, receive the result of the computation from MEC, that is called E of OR. Now, depending upon the energy consumption, so it has to decide about whether to offload or not. So, take this particular example over here. So, if the energy of if the energy consumed in the local is less than energy for offloading, and if the delay is satisfied, then it will perform the local execution. So, here if it is E L is less than E 0 and D L is less than D max, then in that case it will be performing the local execution. Whereas, if let us say that if this is being satisfied, whereas if it is to perform local, then the energy is more than the offloading. So, it will perform the offloading. So, these are the two different methods we have seen for minimization of execution delay and then minimization of energy consumption while satisfying. So, this example shows that that user equipment decides to perform the computation locally, since the energy is spent by the local execution, that is E L, is significantly lower compared to the energy required for transmission reception to the offloaded data. Now, contrary, if you see the user equipment 2 offloads the data to the MEC here, as the energy required for the computation offloading is significantly lower than the energy is spent in the local computation. Therefore, overall execution delay would lower if user equipment 1 offloads the computation to MEC, and also if user equipment 2 performs the local execution, the delay is still below the maximum allowed execution delay constraint, that is, it satisfies the constraints. So, what we have seen is in this example that based on the criteria of minimizing the energy consumption while satisfying the execution delay constraint, we can decide whether to offload to the edge that computation, or we have to do it locally in the user equipment. So, let us see the trade off between the energy consumption and execution delay. So, in this case it is assumed that the computation offloading decision for a multi-user multi-channel environment has to be made considering the trade off between the energy consumption at user equipment and execution delay. Now, whether the offloading decision prefers minimize energy consumption or execution delay is determined by weighing parameters. So, the main objective is twofold: choose if the user equipment should perform the offloading to the MEC or not, depending upon the weighing parameter. In case the computation offloading, select the most appropriate channel to be used for the data transmission. So, the computation offloading decision is done in a sequential manner. In the first step, the user equipment decides whether to offload to the applications to the MEC or not. In the second step, MEC evaluates if it is able to satisfy the request or the computation should be further relayed to the CC. So, the problem is usually formulated as a optimization, convex optimized NP hard, and therefore, these kind of offloading, that is often multiple user equipments assumed to be connected to the same edge node. In such cases, the offloading decision may be done jointly by allocation of computing and communication resources to all the user equipments. So, let us conclude this particular lecture. We have discussed, first of all, complete review. We have seen about the MEC strategies, architectures. Then we have started on that MEC architecture, the overview of computational offloading in MEC. Then we have seen the decision making in the offloading process, such as local execution, full execution and partial execution. So, the factors affecting the offloading decisions we have also seen. They are user preference, radio and backhaul connectivity connection quality, user equipment capabilities, cloud capabilities, resource availability at the edge and cloud, offloadability of application, dependency between the application task, offloading decision based on these metrics such as execution time, energy consumption, and often the trade off between the execution time and energy consumption. Thank you.